HCl is hydrochloric acid. Acids donate a proton. Okay, and check out my arrow. This is the most important thing I want you guys to know. Okay, what is it about my arrow here? It only goes one way. Very good. Okay, so this HCl donates a proton, and it gives us the actual proton, which can be H plus or H3O plus. And it gives us the conjugate base, which is Cl minus. Okay. So when, as Bailey mentioned correctly, that this arrow goes, okay, in one direction, what does that mean? This HCl is 100% or 99%, okay? It's really, really powerful source of what? Of acid. Okay? It's a really, really powerful source of acid, almost 100% source of acid. All right. That's why if you look at our lab and the HCl containers that are really concentrated, you know, I'm talking about 16 molar, 18 molar. Those things are very hazardous. They can eat through your gloves, right? So all these 6 strong acids are going to be like this. All right, the second one is HNO3. Anybody know?
Which was the conjugate base and which was the conjugate acid for the HCl one?
Okay, you tell me, Bailey. That's a good question. Something you should know. Which is the acid and which is the base?
The acid is the HCl and the base is the H2O.
Correct.
And on the other side, wouldn't the acid be the H3O and then the base be the Cl be the base?
Correct. Okay, so these are conjugates of each other, and these are conjugates of each other.
I just want to double check.
All right, next one on our list is nitric acid. Check out my arrow. And the conjugate base is NO3 minus. This is called nitrate. All right, we should know these 6. Okay, nitric acid, hydrochloric acid. The third one on our list is H2SO4. This is sulfuric acid. Okay, sulfuric acid. One of these protons, this can donate 2 protons, but I'm just saying the first one is powerfully acidic. It donates an H+, and when it donates an H+, it becomes sulfate, conjugate base, and H3O+. Okay, this is called sulfuric acid. All right, last 1, 2, 3. Okay, number 4. Number 4 is hydroiodic acid. Okay, this is hydrochloric acid, this is hydroiodic acid. Halogens, chlorine and iodine, when you acidify them, hydrochloric acid, hydroiodic acid. And then you get the conjugate base. Alright, next one is hydrobromic acid. Okay, chlorine, hydrochloric acid. Iodine, hydroiodic acid. Bromine, hydrobromic acid. Yeah.
For the sulfuric acid, wouldn't the H still be?
Oh, yes, thank you. My bad. Good job, sorry. Okay, so here's the conjugate base. HSO4 minus. Thank you, Carolina. Carolina. Right?
So for all these acid ones, the arrows are all just one way, correct?
Very good, correct. Okay, so you guys remember what our classmates said, H2SO4, one proton. One proton donates it, becomes HSO4 minus. HSO4 minus, okay? This is, yeah. This is called hydrobromic acid. All right, and then last is perchloric acid. Okay, perchloric acid. Okay, this is called perchloric acid. So know the identity of these 6 strong acids. So why is this important? The last one is perchloric acid. So a couple of things about these 6 strong acids. Number one, they're strong, which means that they are 100%, or you can say very, very strong, 100% or close to 100% source of protons. They really, really give protons and acidify the environment. Here they are acidifying water. That's number one. Okay. Number two, when we talk about the strength of an acid, okay, the strength of an acid is determined by Ka, okay? Ka, which is products over reactants, Ka. What's going on today? Down here. Okay, Ka, okay, this is the acid equilibrium constant. Okay, these have a very high Ka. Okay, high Ka. Remember, products over reactants. What is the Ka for this? It's not an equilibrium. So first of all, it's overwhelmingly products. That's why the arrow is overwhelmingly one side. Okay, very little goes that. In fact, we ignore this back reaction, and it's overwhelmingly 99 to 100% this way. So this implies a strong Ka, which means a very low pKa. Okay, pKa is the power of the Ka, and pKa is minus the log of Ka. Alright, so all of these 6 strong acids will have a large Ka favoring the products, and because of minus log Ka, it means the number pKa will be low. So on an exam, when you rank acids, which would be the most acidic? Which would be the strongest acid? Okay, the strongest acid would be the one that has the lowest pKa, but highest what? Ka. Okay. So this is how we rank our acids. Okay. Now the next important point here is this. If these are strong acids, do we need an ice table? Check out my arrow. Since the arrow is going so overwhelmingly to the forward side, since it's also going over 100%, 99 to 100% going this way, you don't need an ice table. Yeah? No ice table. So what do you do? How do you calculate the pH? Okay. You just plug it straight in. just plug it straight into the pH equation for these 6 strong acids. Into this to get pH. Okay, only these 6. Okay. What happens if I ask you the pH of, what is the pH of 1 molar hydrochloric acid? Okay, how will you find the pH of 1 molar hydrochloric acid? What is the H plus concentration? It's 1 molar because it's 100% source of H plus. So you just plug it straight in. Okay. So what is the pH of 1 molar acetic acid? Acetic acid. Do you guys know what acetic acid is? Like it's in vinegar? What is the pH of 1 molar of this? Is it a strong acid? No. So here you need an ice table with the Ka. With the Ka value that I will give you on the exam. But on the flip side, let's say we're taking an exam and I ask you what is the pH of 1 molar HNO3, what will the answer be? Is HNO3 a strong acid? It is in our list as a strong acid. It is one of our 6 strong acids. So how will we calculate the pH of that?
Plug it straight into the equation.
Very good. pH is minus the log of 1. Okay, which whatever that number is. Okay. So plug it straight in. 0. The pH is 0. Okay, it's really low pH. Okay. Yeah. Okay. So if you see these 6 strong acids, what will you do?
You plug it into the
Okay. What if it's not one of these 6?
ice table.
Yes. It's not one of these 6, you will put it in the ice table. Okay, and we'll do some of those. How do you know which one goes into the ice table and which does not? How do you know, Bailey?
It's like you repeat that?
How do you know when to use the ice table or not?
Is it when there isn't like an H to donate?
So you have to calculate the pH of a weak acid and a pH of a strong acid. So which one will you use a ice table for? Weak acid. How do you know it's weak? It's not one of these 6. Excellent. Okay, it's not one of these 6. But if it's one of these 6, just straight up plug it in. Okay? Like on page 9 of our notes. Let's go to page 9. So make sure you just know this. All right, let's just go ahead and start off with these problems here. Okay, calculate the pH of an HNO3 solution whose concentration of H3O plus or proton is 0.76. So how will I calculate the pH of this? Is HNO3 a strong acid or a weak acid? Because it's a strong acid, just plug it in. Okay, plug in, chug. You heard this term, plug in, chug? Okay, for it's a strong acid, plug and chug it. What is the concentration of H3O plus? Again, we're assuming close to 100% or 99% ionization, so it's just going to be minus the log of 0.76. And what is that on our calculator? Minus log 0.76, 0.12, okay? Is the answer. So Another thing, pH has no units, it's just a scale. pH has no units, it's just a scale. All right, how about this problem here? The pH of a certain orange juice is 3.33. Calculate the H plus concentration. Okay, so this is not a strong acid, weak acid. It's just telling us that the pH is 3.33. Let's back calculate the hydrogen ion concentration that corresponds to this pH of 3.33. Okay, I'd like for you to know this equation, right? Because you'll probably see it again and again, and it's good to know. But how do we reverse and get the H3O plus concentration? Okay, it's going to be the antilog, and the antilog is 10 to the power of the minus pH. So 10 to the power of minus 3.33. So this is what you want to put on your calculator. Okay, so antilog is nothing more than shift log on your calculator, and it's minus the pH, so minus 3.33, negative 3.33, and it's going to be 0.00046, I'll do 3 sig figs, 467 units. Okay, what are the units of the bracket? Molar, moles over a liter. So 0.000468 molar. Alright, so concentration of protons in orange juice is 0.000468 molar. Okay, moles over a liter. What's the pOH of the orange juice? Anybody had orange juice this morning? What's the pOH of that? How do we calculate this? Go ahead, Maria. You don't need to use an ice table. What's the pH-pOH relationship? They equal 14. pH plus pOH is equal to 14. Okay? Remember this? Or was it because it's before the exam? We don't remember it. Okay, remember this relationship? Okay, pH plus pOH is equal to 14. So what is our pH? 3.33 plus pOH is 14. So pOH is going to be, what's 14 minus 3.33? 10.67. That is our power of OH, hydroxide. Okay, the power of H plus acid is 3.33 given to us in the problem.
So why is it 10.67? I think I missed that part.
Because pH plus pOH is equal to 14.
Oh, so you subtract that. Okay.
Utilizing this equation, yes. Alright, let's look at this table here, okay? So generally speaking, pHs go from 0 to 14, though if you're like super acidic, it can be negative. If you're super basic, it could be above 14. But generally it's a scale that goes from 0 to 14. So remember, how do we back calculate to get the concentration? It's 10 to the power of minus pH. Okay. And then how do we get the pOH? pH plus pOH is equal to 14. Okay. So if you have a pH of 7, this corresponds to a concentration of 1.0 times 10 to the minus 7 molar. And that's a pH of 7. What's the pOH going to be? Okay, it too will also be 7. And then you figure out the concentration of the pOH, or the OH, which is 10 to the power of minus pOH. Okay, and basically what you're seeing here is that it is neutral. Okay, so you have equal amounts of acid, H plus, and equal amounts of base, OH minus.
So the 10 to the negative pH, that's how you get pOH, correct?
That's how you get the concentration of OH.
Okay.
So here, you notice you're getting more acidic. What's happening to the H plus concentration? It's getting higher, 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 and higher. What's happening to the OH concentration as the H plus concentration gets higher and higher? This gets lower and lower. You see this? Okay. Remember, H3, H plus times OH minus equals KW, which is 1 times 10 to the minus 14. Okay, at 25 degrees. So here, as the pH is getting higher, okay, the concentration is getting higher, okay, this way, but what's happening to your pOH? Your pOH is getting lower, okay? You guys see this trend? Okay. Let me just say here, as your pH is getting lower, this should be lower here. Okay, as your pH is getting lower, your concentration is getting higher and higher, your pOH is getting lower and lower, and your OH concentration is getting higher, so this should be higher.
So we have to memorize the table?
No, I just want you to know the trends. I just want you to know the trends, okay?
So the trend is says pH gets lower.
The trend is this, I'll write it down. As your pH gets lower, okay, your H plus concentration gets higher. Okay, that's it.
So everyone, the pH gets lower, H concentration gets higher?
Mm-hmm. And as a result, the OH minus concentration, which is our base, gets lower. Okay. Now the reason why as this gets higher, the acid, the base gets lower, is because number one, pH plus pOH is equal to 14, and number two, the product of these two is equal to KW, which is 1 times 10 to the minus 14. Okay. So this is what I want you to know. Now, as your pH gets lower, your pOH is going to get higher because pH plus pOH is equal to 14. And as your pOH gets higher, what does that mean? As your pOH gets higher, what does that mean? Your H plus gets lower. and then your OH minus, as your POH gets higher, your OH concentration also gets higher. Okay. Again, this is the same reason, because pH plus POH is equal to 14, and the concentration of H plus times OH minus is equal to 1 times 10 to the minus 14. Yeah. I think this is right. So your pOH gets higher, your OH concentration gets... Yeah. Okay, we're usually a pH centered universe, so this is what we should focus on. Okay, pH is lower, means higher, it's more acidic. All right, let's just go back and do these problems. All right, the OH concentration of a blood sample is 2.5 times 10 to the minus 7. What is the pH of blood? Okay, the OH minus of a blood sample is 2.5 times 10 to the minus 7. What is the pH of blood? So what should we do first? Should we calculate, how will we calculate this? Yes, we will calculate the pOH, okay? Which is minus the log of the OH minus concentration. Which is minus the log of 2.5 times 10 to the minus 7. What is that on our calculator? Okay, getting about 6.60. Okay, that's not our answer. Okay, what is our answer? Okay, so that's the pOH. So how will we get the pH? Okay, what is that relationship again? pH plus pOH is equal to what? 14. So we got our pOH is 6.6, so 14 minus 6.6 is equal to pH. So our pH is, what's our pH? 7.4? Yeah, 7.4. Okay, so this is our answer. Anybody here a biology major? 7.4 is actually, I think, the normal pH or cellular pH inside the cell. So, or they call it physiologic pH. All right, which is more acidic, a solution whose H plus concentration is 2.5 times 10 to the minus 3, or a solution with a pOH of 11.6? Okay, which one is more acidic to you guys? Okay, how will we solve for this? What we can do is we can, which is more acidic. So what does more acidic mean to you? More H plus, right? So more acidic would mean a more concentrated H plus, but that also, as we've found out, a more acidic also means a lower pH. Okay, this is the correspondence. Okay, low pH, high concentration of acid. So what I could do here is I'll take the pH of this, and I'll get the pH of this. So what is the pH of this substance, whose whose pOH is 11.6. Okay, I will subtract 14 and get 2.4. What's the pH of minus the log of 0.0025? 2.60. 2.60. So which is more acidic, number 1 or number 2? Which one is more acidic? The correct answer is number 2. Okay, this solution is more acidic. Okay, lower the pH, the more acidic it is. Another way you can do it is you can straight up calculate the H plus concentration. Right, so the H plus concentration for this is 2.5 times 10 to the minus 3 molar. Okay, what's the H plus concentration for this guy? Okay, how do we get the H plus concentration? Okay, 10 to the minus pH, very good, 10 to the minus 2.4. So what's 10 to the minus 2.4? 0.00398. So this is 0.00398. Or 4 times 10 to the minus 3. So which is more acidic, has more protons, the one that's 2.5 times 10 to the minus 3 or the one that's 4.0 times 10 to the minus 3? Okay, obviously the one that is 4.0 times 10 to the minus 3 is more acidic. It has more protons. It's more concentrated than the one that's 2.5 times 10 to the minus 3. Okay. So however you put it, this one is most acidic. Alright, so let's move on here. Alright, so we already went over our 6 strong acids, okay, on page 10 of our notes. So just as a reminder, look at the arrows. Okay, I just want you guys to be aware of the arrows. If there's any back reaction, it's very small, and that we essentially ignore it. So the arrows are in one direction. It's essentially 100% ionized for these 6 strong acids. And what do we say? What do we have to do to calculate the pH? Okay, plug it into the equation. Okay, just straight plug it in. Just plug it straight in. All right, we'll contrast that with page 11, which are just a small collection of weak acids. Okay. So there's hundreds of acids, okay? But if there's 6 that are strong, the rest are, what are the arrows for these? The arrows, they're back and forth. Okay, so here, in contrast to the 6 strong acids, we need an ice table to calculate pH. All right, and then look also here. Okay, look at the Kas. Right, they are less than 1. Yes. Okay. What are the Ks for strong acids? What would they be? Okay. They would be greater than 1. Okay, they'd be very large. So here we're looking at small Kas for the weak acids. Okay, what are we saying for the strong acids? Large Ka. Or low pKa. what are we saying for the weak acids? Everything else, we are saying small Ka, large pKa. So that's the trick. All right, now let's do some ice tables together. Page 13. Let's just check out some things here.
So we write down like those weak acids in the notebooks.
Just the strong ones, because everything else is weak. All right, so I'm going to teach you something here that will make your life a little bit easier. So let's just follow along here. First of all, for weak acids, we'll do something called the low ionization assumption. So first of all, for weak acids, number one, we're going to use our ice table. Okay, so if you know your ice tables from yesterday, or what is it, Tuesday's exam, well, that's good because you'll do a lot of them now. Okay, you'll take the X that you find from your ice table, you divide it by the concentration in the bottle, or the concentration they give you in the problem. And if it's less than 5% ionization, you can use the low ionization assumption. That means very little goes in the forward direction, which basically means no quadratic. But we're not doing the quadratic anyways, so. Okay, if you take the X from your ice table divided by the concentration given in the problem, and you multiply by 100 to get a percent, and you find that the concentration is greater than 5% ionization. That means the reaction is moving forward greater than 5%. Then you have to use the quadratic. Once again, we will not use the quadratic, so we're only going to deal with situations as in the above. Okay. All right, so what does all this mean? Okay, this will make more sense when we do a practice problem together. So let's do a practice problem together. Okay?
So like the second one about like where it says it's more than 5%, we don't need to worry about that one. We have to
If it's less than 5%, you don't have to use the quadratic. But yeah, you won't get problems like this. Okay, that's what you're saying. Yeah.
Yeah, so we don't need to write that one down.
So what is the pH of a 0.122 molar monoprotic acid whose Ka is 5.7 times 10 to the minus 4? Okay, monoprotic. What does monoprotic mean? How many protons does it give off? 1. Okay. So the first thing that we want to do here is we want to write our equation. You guys know the equation? Okay, you should know this for the exam. Okay, any acid. Okay, we're going to write the equation. The equation goes like this. This is HA for any generic acid. Okay, it's going to react with water. And it's going to donate that proton to water in the reaction. Okay. Because it's a weak acid, we'll put our double arrows. It's not strong acid, not one of the 6. And they tell you the Ka here is 5.7 times 10 to the minus 4. So we want to find the pH of this bottle of acid. We call it HA. And we want to find the pH of it. Okay. So what does this mean? Let's say we have a bottle of 0.122 molar HA. Okay, it's a weak acid, okay, not strong. Okay, what else is contained in this 0.122 molar bottle of HA? What else is in this bottle? Is it just 100% exclusively HA? What else is in here? Okay. you have to realize this HA is not just HA in the bottle. What else is in here? Okay, water, but what else? Okay, some of this HA will react and give you H3O plus and A minus, the conjugate base. All right. So this 1.122 bottle of HA is not 1.22 or 0.122 molar HA. There's some of acid in there, and there's some A minus in there. Okay, of course, water is the solvent. Water is everywhere. So this is our Ka. It's a weak acid. It's not one of our 6. It's just any old HA acid. So we're going to do the ice table. All right. So initially we have 0.122. Okay, water is a liquid. Okay, so it's not going to be in our equilibrium. And initially this is 0 and this is 0. Okay, the change is going to be minus x plus x plus x. This is what you're going to do for a weak acid. So at equilibrium, this will be 0.122 minus x, x, and x. The next step is we'll plug it into the equilibrium expression. This is what I want you guys to do for your homeworks and your tests and so on. Okay, we want to plug this into our equilibrium expression. Okay, so this Ka is H3O plus times A minus divided by HA. Okay, we're going to plug those values in. So Ka is given to us in the problem, right? It's 5.7 times 10 to the minus 4. Okay, H3O concentration at equilibrium, x. A minus concentration at equilibrium, x. X times x is x squared divided by equilibrium concentration of HA is 0.122 minus x. Why did I not put in water? Because it's a liquid. Very good. Okay. All right. Now we're going to solve for x. But to solve for x, if you notice, you're going to have to use the quadratic. First of all, I won't let you use the quadratic in the exam. Okay. But what you can do is assume x is small. This is the low ionization assumption. Okay, assume x, that this x, which is the directionality in this way, assume that it's very small. Okay. Okay, what does that mean if I assume x is small? Okay, this is called low ionization assumption. Very little of it goes to the ions. So that means 0.122 minus x is about 0.122. That's the assumption we make. It's an assumption. Okay, we are assuming that it's less than 5% going in the forward direction. That is to say, less than 5% ionization. Okay, so this is what I want you to do on the exam. 5.7 times 10 to the minus 4 equals x squared divided by 0.122. Okay, this is called the low ionization assumption. Okay, so now we'll solve for x here. 5.7 times 10 to the minus 4 times 0.122. We'll square root that to give us x. Okay, I'm just skipping a bunch of steps here.
So like a small x, like a negative x there, do we just get rid of that because we're assuming it's small?
We're assuming this value of x is small.
And that means that we just ignore that when we're solving for it, right?
Correct. All right. So 5.7 times 10 to the minus 4 times 0.122. Okay, square root of this. Okay, I'm getting an x of 0.00834 molar. Okay, 0.00834 molar. But what is that? What is that? That is x. But what is x? Okay. I want to convince you guys that this x that we solved for is the concentration of H3O plus. It also is the concentration of A minus. Okay, so 0.00834 is x. X is concentration of H3O plus. Okay, what is the pH then? pH is minus the log of H3O plus. Which is minus the log of 0.00843. And what is that on our calculator? All right, I'll do that quickly here. 2.07, 2.08. Okay. And that should be the answer, but what did we do? We made an assumption here. Okay, let's test our assumption. Okay, let's test the assumption. Okay, and going from here to here. How will we test our assumption? Okay, what's the threshold? Okay, the threshold is 5%. If this is greater than 5%, then the threshold greater than 5% ionization, then we can't do this. All right? So we'll take our x. What is our x that we just found? Okay, 0.00843. Okay, what is the concentration of the acid? What's the concentration? 0.122. Times 100. Okay, we're looking for less than 5%. Okay, so I'm writing here testing low ionization assumption. Testing our assumption. 0.00834 divided by 0.122. It's 6.8%. So did we pass? This is 6.8% ionized, this acid at this concentration. Okay, what's the threshold? 5. Okay, so the assumption didn't work. You will not see this on the exam. You don't, okay? But essentially, what do we need to do now, since the assumption failed? Okay, since the assumption failed, you have to use the quadratic, which you don't have to do on the exam, but I went ahead and did the quadratic. All right. So what is the threshold? 5%. How do we calculate that? Okay, you take the x divided by the concentration in the bottle, and it should be less than 5%. Okay, so this assumption did not work. Use the quadratic equation, but you don't have to do that. I'll give you it where it's less than 5%. Okay, do you guys understand me? Okay, so you'll be in situations where it'll be less than 5%.
So when you use the quadratic, you usually get a false E minus.
Yes.
You take the square root. How does that? What does that mean? That you have a plus and minus?
You will reject the negative.
Oh, okay.
You'll get a plus and minus, and one of them, when you plug it back in, this is a good question actually, Maria. When you plug it back in, you'll get negatives. You reject that one. You accept the x that when you plug it back in, it'll give you positive, because there's positive concentrations. There's no such thing as negative concentrations. Having said that, you won't do this on the next. Okay? You're just going to do all of this, and it will be less than 5%. Okay, how do you know? Okay, you plug it in here, but I'll give you problems where it's less than 5%. Just, if it's over 5%, you got to do the quadratic. All right, because it was 6.8%, and was greater than 5%, I did the quadratic there, and you can check that out. Let's see what's this here. All right. I did an ice table on water. Okay, I did an ice table on water. Usually the concentration of water in 1 liter is 55 molar. Okay, so 55 molar. Okay. And when I did that, so you don't need to know why it's 55 molar, but I can just show you here. Let's assume the density is 1 gram per mil for water. Okay, 1 mole of water is about 18.04 grams of water. And then there's 1,000 milliliters in 1 liter. Okay, so the mils cancel, the grams cancel, and when you do that, 1 liter of water has 55 moles in it, so 55 molar. So if you take 1 liter of water, put it through this ice table, and run it through the KW, you'll get a percent ionization of 0.000018%. Okay. So what does this mean? It means that water is a very poor source, if it's pure, a very poor source of H plus and OH minus. It is a source, and like in biochem they say it's important in the mechanisms, but it is a source of H plus and OH minus, but it's a very poor source. And I think I told you guys, I read this. A lot of things escape my mind, like one ear out the other. But this one stuck with me. Like for the, let's say you have 1 liter of water. For every trillion water molecules, one will go this way and give you H3O plus and OH minus. For some reason that stuck to me to this day. So you have 1 trillion water molecules. Out of that trillion, how many will do this reaction? 1. And that 1 water molecule out of 1 trillion will go this way and give you H plus and OH minus. Okay? So that's a very, very small amount of ionization in water. However, in biology and biochemistry, that's very important, okay, in the biology realm. All right. So what did we cover here? We covered low ionization assumption. Okay, we assume it's less than 5%. Okay, and that's the type of problems I'll give you on the exam. Less than 5%, so you do not have to use the quadratic. Water can self-ionize, self-protonate, and that's a very small amount of ionization. Okay. All right, I think I will stop on page 16 here. Okay. I'll stop on page 16, and then next week we'll finish this chapter up and then move on to chapter 16. All right, so. Okay, so just give me 10 more minutes here. So let's review here. What are our strong acids? 6 of them. Can you name them for me? Hydrochloric acid, perchloric acid, nitric acid, sulfuric acid, HBr, the halogens, HClO4. Okay, perchloric acid. Okay, so what did we say about these strong acids? 100% ionization. Plug to get the pH. Okay. No ice table. ice table. Okay, what are our weak acids? Okay, what are our weak acids? Everything else, okay? So let me give you a classic weak acid, okay? Stereotypical weak acid, and that would be acetic acid. Okay, anybody, have you heard of acetic acid? There's many more, okay? There's many more, but acetic acid is one of them. And this has a Ka of whatever the Ka is, okay? You look it up in the book, okay? So what do we know about acetic acid and these other types of acids? Actually, the Ka for acetic acid is 1.75 times 10 to the minus 5. So I'll put here plus all other weak acid because it's an entire list. I'm just giving you a classic example, acetic acid. Okay, what do we know about weak acids? What should we do? Use an ice table, and we can use low ionization assumption, less than 5%. Okay, use low ionization assumption, LIA. Okay, so these are our weak acids. Okay. All right. Next, we want to put in this list the strong bases. Okay, SB. What are our strong bases? Basically anything with OH minus. Okay. That's a strong base. You can see some of them on this list here. Okay, NaOH, KOH, barium hydroxide. Okay, so the strong bases are group 1 and group 2 hydroxides. Group 1, lithium, sodium, potassium. Group 2, barium, magnesium. Okay, so these are our group 1 and group 2 hydroxides. Okay, what do we know about our strong bases? If a weak acid, if a strong acid is 100% ionization to H+, what is a strong base? Okay, it's 100% ionization to OH minus. 100% ionization. So how will we get the pH? Before we get the pH, what should we get if it's a strong base? We plug it into the pOH.
So it is also 100% ionization, like strong acid, but with OH, correct?
With the base, okay?
The base,
Yeah, and no ice table. All right, and then we have our weak bases.
You also need us to memorize the strong base as well.
That's easy. There's just NaOH, KOH, LiOH, just OH
So we don't need
minus.
to memorize them.
It's easy, AOH minus, okay? All right, what are some weak bases? Do you guys remember the amines? Okay, there's a functional group called the amines. NH3. Okay. NH3 is an amine. Or ammonia. Basically, the functional group, the amines, ammonia. You can see some on page 17, okay, on your notes. So these weak bases are a weak source of OH minus. These weak acids are a weak source of H plus. And what do we do with the weak bases? use an ice table. And we use the low ionization assumption. Okay? What will we find first? We will find POH first. Okay? Because these are a weak source of OH minus. Okay? So while the weak acids are a weak source of H plus, these weak bases are a weak source of OH minus. Okay. Do you know ammonia? This is really interesting. Not many people know this. Ammonia is a source of OH minus. And here's that equation. This is your classic example of a weak base bump. Not many people know this, okay? Not many people know the ammonia that you buy from your store or wherever can actually give you OH minus. It is a source of OH minus. It's a weak source of OH minus. 5.62 times 10 to the minus 10 for the KB. Okay, so here water is donating the proton. The NH3 takes it, it abstracts that proton, it gives you the conjugate acid NH4 plus, and there's that OH minus. Okay, so bottom line, NH3 is a source of OH minus, but it's a weak source. Okay, it's a weak source by the KB value given to us in our textbook. Weak base. Another thing here, look at the arrows. Okay, very small KB value, back and forth. This does not go to 100% completion. What will go to 100% completion? Okay, the group 1 and group 2 hydroxides. Powerful source of OH minus. And these are your strong bases. Okay. Alright, so calculate the pH of 0.018 molar solution of barium hydroxide solution. So what is barium hydroxide? When you see that, what do you think? Do you think strong acid? Do you think weak acid? Do you think strong base? Do you think weak base? What do you guys think? Okay, what is barium hydroxide in actuality? Okay, barium hydroxide in actuality is barium ion plus not 1, you have to balance this. Okay, plus hydroxide ion, but it's 2 because you need to balance it. Alright, so how will we calculate the pH of this? Okay, barium ion in water, barium hydroxide in water is barium ion plus hydroxide ion. So how will we calculate the pH? What should we calculate first? We can't calculate the pH first. What should we calculate first? Which one should we calculate? POH, correct. Okay, it's going to be minus the log. So it's, okay, so this is tricky, I have to admit. So there's 2 OH minuses, so you're going to take this 0.018 and times it by 2. Okay. You see there's 2 OH minuses, so 2 times, so this barium hydroxide actually in water gives you barium ion and 2 hydroxide ions. So the actual concentration of hydroxide is 0.018 times 2. We plug that in to get us to POH, and what is that number? Uh, 1.44. Okay, that's not our answer. What's our final answer? So what is our pH? Okay, it's going to be, we calculated the POH, so our pH will be 14 minus 1.44. And what is that? 12.56. Okay, very basic pH. 12.56. All right. So I thought we can finish page 16, but I guess not. So have a good weekend. For those of you that came late, a couple of minutes late, I had some announcements. Number one, our lab for Monday and Tuesday is a problem set. I'll give you 2 weeks for you and your group to work on that. And then I'll give you an extra week for this past lab, the solubility product constant. So there's no lab, no meeting on the labs Monday and Tuesday. But please work on those problem sets, and I'll give you an extra week to work on the KSP. Okay? Last Monday, past week's lab. Another thing is work on your chapter 15 homework and turn that in. I'll give you 10 points for that. Exams. Stay here, I'll give you your exams.